At the top, a ratio is a comparison of two quantities by division. What is something else that we've learned about where you have a part and a whole and it's also division? A fraction. So when we talk about ratios, sometimes you will see ratios written like a fraction because you're comparing parts. So ratios compare two quantities. If I was comparing 3 triangles and 4 circles, then what is the ratio of triangles to circles? The way that I can write that, there are 4 different ways to describe a ratio. Well, we just talked about a fraction. Okay, a fraction is usually a part to a whole. But with ratios, I can write a ratio in fraction form that looks like this. 3 over 4. I still read it 3 to 4, but this is describing a part to another part. Now, do you think I could write a ratio for part to whole? If I said girls to total number of students in this class, yes, that's a part to a whole ratio. But if I said girls to number of boys in this class, that's part to another part. There is no total. Okay, so ratios can be part to part or part to whole, like a regular fraction would be. Okay, another way that you can write this is a 3 with a colon in between and then 4. You still read it the same way, 3 to 4. You read the fraction 3 to 4. You read this 3 to 4. You can also write it 3 to 4. And you can also write it all out so it looks like this. 3 triangles. Uh-oh, I spelled that wrong. Triangles. No, you're going to write it out in words because this is how it'll look. So 3 triangles to 4 circles. So it may be written out with the label attached to it, triangle circles. It might just say 3 to 4. It might say 3 colon 4, which we still read as 3 to 4. Or it could be written as fraction. Okay. When you're looking at equivalent ratios, you're going to multiply or divide both terms of the ratio by the same number to find an equivalent ratio. Just like whenever we work with equivalent fractions, if I'm trying to get 3/4 to an equivalent fraction out of 12, then I have to multiply the bottom by 3. And whatever I multiply the bottom by, I got to multiply the top by the same thing, right? So this is very similar. I multiply or divide both terms of the ratio by the same number to find an equivalent ratio. So this is actually called a ratio table, right down here where it says apple pies and cherry pies. So if I'm looking at this ratio table, I want to multiply by the same thing. So it's already showing me times 2, times 3. Imagine this as a fraction, 3 to 7. I want to multiply the top number by 2, so this becomes 6, and the bottom number by 2, so it becomes 14. So a 6 to 14 ratio is equivalent to a 3 to 7 ratio. Okay, well, what if I multiply 3 by 3? It would be a 9, and then 7 by 3 to 21 ratio. The next one would be a 12 to 28 ratio. What would the next one be?
15 to 35.
15 to 35 ratio.
18 to 42.
And then 18 to 42 ratio. So ratio tables can help you see and find patterns, maybe a little easier so that you can predict. For example, if I had 27 apple pies, how many cherry pies would I have? So you could then figure out, looking and identifying patterns, how many cherry pies you would have based on how many apple pies you have. Okay? All right, well, what if I'm given a scenario and I have to find the ratio out of a scenario given to me like below? It says find the ratio, 8 students out of the class of 32 had ice cream at lunch. Okay, well, what does that look like as a ratio? It would be 8 to 32. Had ice cream. Could I simplify that ratio at all?
1/4.
Okay, so I could divide these by 8, and it would be a 1 to 4 ratio. So 1 out of 4 students, okay? 1 out of 4 students had ice cream at lunch. So how many did not have ice cream?
3/4.
Good. 3/4 did not have ice cream.
I mean, if we had ice cream in the cafeteria, I would eat it.
You would be high there anyways.
So how do I get that? Well, I know the total, everybody, is 32. I can subtract how many I know didn't and end up with 24 out of 32. Or I could take my whole, if I know that 1/4 had it, I could take 4/4 minus 1/4 equals 3/4. That would be another way to solve it. There's several different ways. That's why math is so cool, because there's so many different ways that you can get to the same answer. You can go back to your original information here. Subtract 8 from 32 gives you 24 out of 32 to find your ratio. Or you can do it this way. Okay, here's another ratio table. It says, what is the ratio of blue to green jelly beans? Now, this isn't comparing two quantities yet. What it's giving me is information of all the different color jelly beans, and I'm going to create ratios using this information. So it wants to know the ratio of blue to green. I'm comparing blue to green. What would I write?
7 to 3.
Okay, and I can write this several different ways. I could do it like this, a 7 to 3 ratio. I could write it as a fraction 7 to 3, or 7 to 3. I could also spell it all out. I could say 7 blue jelly beans to 3 green jelly beans, but I don't have enough space. But you can also write it out like that. What about red jelly beans to the total? What would that look like? 6 colon
19.
this is 10, this is 20, this is 5. Total. 25. You still have to include the red. Or I could do 6 to 25. Or I could do 6 to 25. Now this is considered a part to whole ratio because I'm talking about the total. Okay, so remember, you can have part to part, you can have part to whole. All right, any questions so far? Okay, let's look at the next one where we break down and see what equivalent ratios might look like. Okay, I'm going to make the left side bigger first. All right, equivalent ratios are ratios that make the same comparison and we can show equivalent ratios using what we call a tape diagram or a double number line. So tape diagrams use one bar to represent one quantity. Tape diagrams use one bar to represent one quantity in a ratio, but it also uses a second bar to represent the other quantity. So remember, ratios are always comparing two quantities, two different things. So if I have a tape diagram model, I'm going to have one to represent one of my quantities, and I'm going to have another one to represent the second. Okay, but I also have something else called a double number line. So we're going to look at both of these. A double number line is a number line on top to represent one quantity, and a number line on bottom to represent the other. Now there are something called tick marks. The tick marks are the little marks along the number line. So the tick marks align, they line up to show equivalent ratios. Okay, so we're going to look at tape diagrams first. My example says a camera recorded 4 pygmy rabbits and 1 long-tailed weasel. What is the ratio of pygmy rabbits to long-tailed weasels?
41.
Okay, so right now we can see just from the model it's a 4-to-1 ratio. Over a longer period of time, the camera recorded 3 long-tailed weasels. The ratio of pygmy rabbits to long-tailed weasels stays equivalent to 4-to-1, my original ratio. Fill in what each tape represents and what one block represents in the tape diagram to model the new situation. Okay, so if this originally was my 4 pygmy rabbits and this is my 1 long-tail weasel, what is this going to represent on top? My pygmy rabbit. So I'm going to go ahead and write pygmy rabbit, or rabbits. There's more than one. And this is my long tail. I'm going to do L dash weasels. Okay, but this is my new situation, and it tells me that the camera recorded 3 long-tailed weasels, but the ratio stays the same. The ratio is still a 4-to-1 ratio. So if it's equivalent, equal, my numbers are changing, but it's still equal. Think about when we work with fractions, okay? If it's 4-to-1, I want to keep it 4-to-1, but instead of each of these representing 1 pygmy rabbit and 1 long-tailed weasel, now I have 3 long-tailed weasels. So then what does each of these also have to be? 3. So each of these would be 3.
That means that one's 12.
So how many pygmy rabbits did the camera record then? 12, yeah. 12 pygmy rabbits. Okay, let's look at another one. Okay, so maybe you're like, ooh, I think maybe I get it, but I'm not sure if I get it. So let's do another one. The ratio of pink roses, Valentine's is coming up. Ratio of pink roses to yellow roses in a flower arrangement is 5-to-3. We are going to construct, which means make, a tape diagram to show how many total flowers are in the arrangement if there are 15 yellow roses. Okay, well, I'm going to need 5 boxes to represent pink roses, and I will need 3 boxes to represent my yellow roses because that is my original ratio. So let's go ahead and draw our rectangles. We'll break it up so that I have 5 sections. This is going to represent what color? Pink or yellow? Pink. And then down here will be yellow. So I'm going to do the same thing. I want to make sure that they line up. Instead of 5 though, I only need 3. So I got to figure out if I have 15 yellow roses, what each one of these boxes is going to represent. How many roses would be represented by each box? 5. So I have 5, 10, 15 total. So each box is representing 5 roses. Okay, well, it's saying there will be a blank total flowers if there are 15 yellow roses. This should say yellow roses. If there are 15 yellow roses, how many total roses are there going to be? Because if each box, if each box is 5, I could write that in here, and I can now see that I have 5, 10, 15, 20, 25, 30, 35, 40 total roses. That is considered a part-to-part ratio or a part-to-whole ratio if I used 40.
Part-to-whole ratio.
That would be a whole because 40 is the total. So if I wrote a ratio that said yellow roses to total roses, that would be a 15-to-40 ratio. What if I said part to part? What if I just want to know my part to part ratio for pink to yellow? It'd be 25 to 15. is, going back to my original up here, 5 to 3, is this equivalent? Think about simplifying. If I were to simplify 25/15ths, I would divide them. Yeah, they're equivalent, same amount. Okay, let's look at a number line, a double number line. Okay, this is representing a number of couches and number of hours. A double number line looks like a table, kind of, because I have my labels off to the side over here, and I have my amounts here. It's just not organized within the table boxes. So I can read this as, for every 2 hours, 5 couches are moved. So to predict how many couches could be moved in 36 hours, I multiply 2. Why would I multiply 2? Because that's my original ratio. I know that every 2 hours I move 5 couches. So if I'm trying to figure out how many couches can be moved in 36 hours, I'm going to multiply 2 times 18 to get 36. So I'm trying to get from here to here. So how do I get from 2 to 36? I multiply by 18. So that means I have to multiply the number of couches, 5 times what? 18 also. Whatever I do to one part of the ratio, I have to do to the other to keep them equivalent. It's just like equivalent fractions. So what this would look like if I set it up as a fraction, it would be a 2 to 5 ratio. For every 2 hours, I move 5 couches. If I'm trying to figure out if I move it in 36 hours, I want to know this missing number right here. So that's where I get the 18. Does everybody understand where I'm multiplying 18, where that comes in? Okay, so then it will take 36 hours to move how many couches? 90 couches. Okay, so we've talked about basic ratios. We've talked about equivalent ratios. I'm going to show you a video, if I can find it, on ratios.